Okay, when we have three variables, things get really big and messy. So if we have three variables, we're going to need three equations to solve the system. The graphing method is too awkward. Trust me, you don't want to graph in 3 dimensions. Substitution would work, but it gets really messy. Elimination's the way to go. And particularly elimination using matrices is really the way to go, and that'll be coming up here in the next section. The result, our solution to the system, if it's a unique solution, is going to be what we call an ordered triple, x, y, and z. We can still have the two special cases, the no solution inconsistent, or the dependent system where we have to describe the solution set in terms of some arbitrary constant. So first example, we really need to be systematic here. So what I'm going to try to do is eliminate first the variable x and then eliminate the variable x and y, and so that my result is kind of an upside down triangle here with a leading coefficient of 1. And so just try to bear with me, and hopefully as we go through the process you can see what I'm aiming for. There may well be some shortcuts, but this is a system that always works. So the first thing I'm going to do is swap row 1 and row 2 so that I've got my system of equations with the leading coefficient of 1 here for the x. Now I'm going to use the first equation multiplied by constants in such a way to eliminate the x from the second equation and the third equation. That's why I want this leading coefficient of 1, so it'll be easy to modify the first equation to eliminate the other two equations of the variable x. I hope this makes sense to you. Okay, so I'm going to take negative 2 times my first equation and add it to my second equation. So negative 2 times my first equation will give me this. Here's my second equation unchanged, and when I add them together, I get this equation that only has y and z. And this is going to be my new equation 2, or row 2 of the system. And then I'm going to take 2 times the first equation and add it to the third equation, because that will give me my 2x and negative 2x, eliminating x from the third equation. So 2 times equation 1, and here's equation 2, and when I'm adding them together, I get an equation that only has y and z. And this is going to be my new equation 3. And so when I rewrite the system here, I still have my equation 1, my new equation 2, and my new equation 3. I'm kind of working towards this triangle. My next goal is going to be to try to eliminate this y here so that I've got an equation with 3 variables, an equation with 2 variables, and an equation with only 1 variable. That's my goal. How I get there, have to be creative. So what I'm going to do is go ahead and swap row 2 and row 3 here, just because I think this will be a little easier to deal with. And then after I swap it, I'm going to multiply this row by negative 1/3 to get my leading coefficient of 1. I thought this would be less icky than multiplying this equation by 1/8. Fractions wouldn't be as bad. So when I do that, multiply this equation by negative 1/3, I get positive y. 1/3 z equals negative 1. So I only have one fraction. And now that I've got that leading coefficient of 1 here, I'm going to multiply this equation temporarily by negative 8, add it to row 3, and get my new row 3. So negative 8 times row 2, here's my row 3, so the y's eliminate, x and negative 7 is positive 1, and then I have to think a little harder here. I know 3 is 9/3, so negative 8/3 plus 9/3 gives me 1/3 z for my new row 3. I think I've got that here on the next page. And then I went ahead and multiplied that by 3 to get z equals 3. So now I've got x and a bunch of stuff equals 2, y and some stuff equals negative 1, and z equals 3. So I know z equals 3. Now I can back substitute to solve. Since z equals 3, if I go to row 2, which only had y and z, let z equal 3 in row 2, and then I can solve for y. Now I know what z is and what y is. Now I can go to row 1, put in my value for y, put in my value for z, and then I can solve for x. And then my solution is what, again, we call an ordered triple, a value for x, a value for y, and a value for z. And so this process is kind of messy, and these problems get long, but again, it lays me down to something where I can easily do the back substitution and get the x and the y. Okay, this one has no solution. So again, I'm going to swap row 1 and row 2 to get that leading coefficient of 1. and then I'll take negative 3 times my new row 1, add it to row 2 to eliminate the x, and then I'll also take negative 1 times my row 1 to add it to the third row to get my new equation 3, and that'll eliminate the x there also. So, okay, one thing at a time, sorry. So negative 3 times row 1 added to row 2 is going to be my new row 2. So negative 3 times my original row 1 here will give me this. And here's row 2. Adding them together, I get an equation just y and z. That'll be my new row 2. And then taking row 1 and just hitting it with a negative, changing all the signs, adding that to row 3. That'll eliminate my x's. And again, I get an equation with just y and z for my new row 3. And then here's my system now, and I think you may be able to see already what's going to go wrong here. Okay, so copied it over again. So now if I just take row 2, subtract row 3, I'm not going to bother this time trying to get my leading coefficient of 1 because I can see it's just going to fall right out at this point. When I subtract those two, I get my contradiction. 0 equals negative 1. So looking at my new system here, my final row says 0 equals negative 1, which is not true, and that means I have the no solution case. Just one more thing I'm going to look at here. It's a story problem, just to let you look at one of them. So over 3 days, I've got 3 trucks hauling cement to a work site. We know on the first day how many trips were made by the first truck, how many were made by the third truck, how many were made by the third truck, and the total amount of cement that was delivered that first day. We have the same information for the second day and the same information for the third day. And then it's really important when you're solving these word problems, pay attention to what you're being asked, because that will tell you what your variables are. If you know what your variables are, it makes it much easier to set up your equation. So if each truck was filled to capacity on each trip, find the number of cubic yards each truck is capable of carrying. So that's what we're trying to find, how much capacity is in each truck. So I'm going to let my variables be A, the capacity for truck A, B be the capacity for truck B, and C be the capacity of truck C. And really this is the same thing as the Marigold problem. 4 trips for truck A plus 3 trips for truck B plus 5 trips for truck C gave us 78 cubic yards of cement at our work site. There's day 1 right there, gives us one equation. On the second day, 5 trips were made by truck A, 4 trips by truck B, 4 trips by truck C, and that gave us 81 cubic yards total for the 3 trucks on the second day. And then on the third day, there were 3 trips by truck A, 5 trips by truck B, 3 trips by truck C, for a total of 69 cubic yards. So I just wanted you to see how they got set up, and then we'll talk more about solving and how to use our calculator to do all the hard work for us coming up next.